We can use the Pythagorean theorem and properties of sines, cosines, and tangents to solve the triangle, that is, to find unknown parts in terms of known parts. Let's look at some cases where we don't know all the sides. Suppose we don't know the hypotenuse, but we do know the other two sides. The Pythagorean theorem will give us the hypotenuse. For instance, if lowercase a equals 10 and b equals 24, then lowercase c squared equals a squared plus b squared equals 10 squared plus 24 squared equals 100 plus 576 equals 676. The square root of 676 is 26, so lowercase c equals 26. Now suppose we know the hypotenuse and one side but have to find the other. For example, if lowercase b equals 119 and c equals 169, then a squared equals c squared minus b squared equals 169 squared minus 119 squared equals 28,561 minus 14,161 equals 14,400, and the square root of 14,400 is 120, so lowercase a equals 120. We might only know one side, but we also know an angle. For example, if the side lowercase a equals 15 and the angle capital A equals 41 degrees, we can use a sine and a tangent to find the hypotenuse and the other side. Since sine capital A equals lowercase a divided by lowercase c, we know lowercase c equals lowercase a over sine capital A equals 15 over sine 41. Using a calculator, this is 15 over 0.6561, which equals 22.864. Also, tangent capital A equals lowercase a over lowercase b, so lowercase b equals lowercase a over tangent capital A equals 15 divided by tangent 41 equals 15 over 0.8693 equals 17.256. When you use a sine, cosine, or tangent, it depends on which side and angle you know. Here is some more trigonometry. The previous page gave you the basic definition of right triangle trig properties. You will have another detailed lesson which will explain some applications of trig later in this course. If you know the length on two sides of a right triangle, you can always calculate the third using the Pythagorean theorem. Likewise, if you know the lengths of two sides of a right triangle, you can calculate the angle using the trig ratios or using the inverse function to go from the ratio back to an angle value. How do we go about solving problems in physics? There are two different problem-solving graphics shown. There are many different methods of problem solving that can occur in physics. Over the following pages, you'll see various ways of solving problems. Click on this link to play the Monty Hall game. After you've played the game a few times, click this link and read the article to get an interesting perspective on what is the best approach to win and why. Solving problems is a major part of physics and one that you should try and think about as you work through this course. To be most successful in a physics class, problem-solving skills need to be developed as the course progresses. Whenever you solve problems in physics, you should create a solution to the problem. In doing so, you should follow the strategy outlined here. This includes reading the problem carefully, drawing a diagram and visualizing what happens, then identify the principal information needed in the problem, such as list the data and make multiple representations of the problem terms. Choose equations to use and then solve the equations. Eventually, you should evaluate the answer and check it to determine if it is reasonable. It is important to realize that a solution to a problem in physics usually isn't a single answer, but rather the process that it takes to get the answer. If an employer asks you to solve a problem, they usually don't want a simple answer like yes or no. They want a well-thought-out, developed answer to the question or task that was given to you. There is no single problem-solving procedure that will solve every possible problem. However, here is one that works in many situations. You should feel free to adapt this procedure so that it works best for you. Remember, you would always want to keep your destination in mind so that you didn't miss your exit and become hopelessly lost. Make sure you are answering what the question asked for. Consider this. If you were told to drive to Exeter, Nebraska, the first thing you would do is get a map, figure out where you were on the map and where you need to go to. Then you would go about trying to plot a course between your 2 points. You would always want to keep your destination in mind so that you didn't miss your exit and become hopelessly lost. The same is true for solving problems. Let's try a practical problem-solving example. A cylindrical container with a height of 28.5 centimeters and an inside diameter of 10.4 centimeters is filled completely with water. What is the mass of the water in kilograms? Plan out the steps for a solution and solve this problem on your own. Then check the next page when you are finished to see if your solution to the problem is correct. The last step in solving a problem should always be checking to make sure that your answer makes sense. In doing this, a good start is to check your units. The correct answer to this problem has units of kilograms, which is a valid unit of mass. Had the unit not worked out, the number attached to it would not be correct either. The next thing to do would be to decide if 2.42 kilograms seemed reasonable for a cylinder of water that is 28.5 centimeters tall and 10.4 centimeters wide. These dimensions correspond roughly to a 2-liter bottle. A mass of 2.42 kilograms has a weight of a little over 5 pounds. Does a 2-liter bottle of your favorite soda weigh about 5 pounds? It would seem that our answer is of the correct magnitude. Notice that the statement of the problem never said that the density of water is 1,000 kilograms per cubic meter, nor did the problem tell you which formula to use to calculate the volume of the container. The words water and cylindrical were clues to these 2 pieces of information. You must be ever alert for implied clues when solving problems. For example, when we begin modeling motion in the vertical direction, problems do not include a statement to the effect of, "Oh yeah, don't forget about gravity." You must rely on your experience and common sense as well. As an example of how to apply general problem-solving techniques to the type of problem you might encounter in physics, we will consider the following situation. Returning home from a much-needed long weekend getaway, you drive at a steady 65 miles per hour for 3 hours. At that point, a heavy rain begins to fall, and you must reduce your speed to 50 miles per hour. It takes you another 2.5 hours to get home. How far away from your home was your weekend getaway location? What was your average speed on the trip home? Draw a sketch to illustrate the situation. This helps to clarify the situation so that it is clear in your mind. Write down all of the information given in the problem using the symbols appropriate to each quantity. For example, if one of the given quantities is time, you might label it as t. Write down the quantity or quantities you are trying to find. These are your unknowns. Decide which mathematical relationships fit the situation. In other words, what equations will you need to solve the problem? Write these equations down. Solve the problem by substituting the known quantities into the chosen equations and solve for the unknowns. Evaluate your answer. Does it make sense? Are the units correct? To see how these steps work, we will apply them to the previous example. Step 1, draw a sketch. Step 2, list the given quantities. In this problem, we are given 2 speeds and 2 times. We will list them with subscripts to distinguish between them. Step 3, list the unknowns. In this problem, we are looking for 2 things: the distance traveled and the average speed. Choose the appropriate equations. Since the problem indicates constant speeds for both sections of the trip, we can use the basic distance formula learned in algebra class for the first part of the problem. D equals V times T. For the second part of the problem, we need to know how to determine average speed. The mathematical definition of average speed is total distance divided by total time. Step 4, solve the problem. Since there are 2 parts to the motion, the first part of the problem will need 2 steps to solve. For the first part of the motion, 65 miles per hour times 3 hours equals 195 miles. For the second part of the motion, 50 miles per hour times 2.5 hours equals 125 miles. This makes the total distance, d1 plus d2, equals 195 plus 125 equals 320 miles. For the second part of the problem, we note that the total distance traveled was 320 miles, while the total time of travel was 5.5 hours. The average speed for the trip was 320 miles, divided by 5.5 hours, equals 58.2 miles per hour. Always make sure you evaluate your answer. The answers are of a reasonable magnitude and the units are correct, so the answers are probably okay. Note, in case you thought you could solve the average speed part of this problem the way you average grades, you can't. You can't just add the 2 values of speed and divide by 2 to get an average speed. This is because the time frames for each speeds weren't the same. We will review this concept in greater detail when we discuss kinematics in future lessons. Your assignments for this lesson include reading Chapter 1 in your textbook, looking at Chapter 1 problem sets, and any kind of Chapter 1 lab activity or capstone activity. In this lesson, you covered the following objectives.